Welcome, everybody. Today's talk in the PALS seminar is Local Finiteness in Varieties of MS4 Algebras by Chase Meadors. Chase?
All right, thanks. Yeah, so that's what the talk is about. Most of this is based on joint work with Garan Bezanishvili. Here's a brief outline of what we're going to do. All of this is motivated by results that are known for S4 algebras. So we'll talk about what those are. And then we'll go over duality for these algebras. And then finally, we'll talk about monadic S4 algebras. And finally, this final section on M plus S4 algebras. So an S4 algebra is just a Boolean algebra with one additional unary operator that we traditionally write with a diamond. So it's this kind of a tuple where B is a Boolean algebra, and I'll use this notation for the Boolean operations. And this diamond is just a unary operation on B, and it's a closure operator. So that's what these four identities here say, is that diamond is just a closure operator. And it is equally well, I could have written, in the abstract I mentioned that these are also called interior algebras. I could also write this box, which is just not diamond not, and that would be an interior operator. Which one you choose to take as native is up to you. They're interdefinable over Boolean algebra. So why would we care about these algebras? For me, I think of them as providing algebraic semantics for a kind of modal logic, which is just the modal logic with these axioms here on the left. And I just want to make a note that throughout the talk, I'm going to conflate formulas in thinking of them as logical statements with terms. Right, and this is the basic idea of algebraic semantics here, is that the algebra is designed so that formulas are just terms in the signature of this algebra. And if I ever say that an algebra validates an identity phi, what I actually mean is it validates the identity that says phi is equal to 1 in this algebra. We're also over a Boolean algebra, so in fact inequalities are equalities. So statements like phi is less than psi are actually an identity in the setting of a Boolean algebra. And implication is right. I validate an implication exactly if I validate this identity that says phi is less than psi. Right, so from an S4 algebra, there is this thing you can do if you look at the box fixed points. So box, remember, was an interior operator, so it's idempotent. And if you look at the fixed points of box, then those will be a bounded sublattice. And in fact, this sublattice has the structure of a hiding algebra. You can define this hiding implication by the just box of what we think of as the normal material implication in a Boolean algebra, not A or B. This is basically related to an algebraic proof of the Gödel translation that translates intuitionistic logic into the modal logic S4, right? This is the underlying idea of that. So I want to go over basically Stone duality and then Janssen-Tarski duality to show how I actually think about these algebras. So for that, I want to motivate Stone duality in a particular way. So surprising absolutely no one here, any set gives rise to a Boolean algebra, right? Just by taking the power set. And one way to think about Stone duality is that it gives you a representation theorem in the converse direction. So in fact, every Boolean algebra is representable as an algebra of sets, right? A subalgebra of some P of X. And so it's representable as a subalgebra. If you want to identify exactly which subalgebra, then you need to put a topology on the set X, and then you can identify exactly what the algebra is as the set of clopens in this topology. So how you implement this duality, right? So if you give me a Boolean algebra B, I can look at the ultrafilters, and this map that sends an element A to those ultrafilters that contain it will be an embedding, a Boolean algebra embedding of B into P of X. But these S of A's actually generate, they are a clopen basis for a Stone topology, which by that I just mean zero-dimensional compact Hausdorff. And so B is exactly isomorphic to these the Cloven subsets in this topology. That's how you identify the image of the embedding. So I want to now contrast this. So I've told you how Boolean algebras can arise. Let me tell you how S4 algebras can arise. So the situation now is mostly the same, but except instead of starting with a set, I'm going to start with a relational structure, say X comma R. All right, we'll say R is a transitive reflexive relation. When I have a structure like this, I get an S4 algebra out of it by taking, again, the power set and then using this relation to interpret this unary operator. So it turns out that this diamond R that I've defined, if R is reflexive transitive, that's sufficient to make this diamond R a closure operator. And so in this way, we get an S4 algebra. And Janssen-Tarski duality can be viewed as giving you the representation theorem in the other direction, that in fact, every S4 algebra is representable in this way as an algebra of sets, algebra of subsets of a relational structure. And again, you put a stone topology on the set X to figure out exactly what the image of your embedding is. So the implementation is exactly the same. I again take the ultrafilters. You can define a relation between the ultrafilters that I'm not going to bother motivating in this talk, but you can do it. You can put a relation on them in that way. It will be a quasi-order. And you can get this embedding of A into the power set. And to identify the image of the embedding, right, you put this stone topology on X, and your S4 algebra is exactly the set of Clovens in this topology. So this relation that was constructed there will actually turn out to have some special properties. It'll be compatible with the topology. It'll turn out that the set of points that are seen from any point X is closed, right? So R of X is going to be, we call that point closed. And that R inverse will take Cloven sets to Cloven sets. Now, the first condition may seem a little mysterious, but the second one is exactly what it means for a function to be continuous, and so it's natural to call this a continuous relation. So if we have a relation on a stone space like this, we call it continuous, and a relational structure where this happens, where X is a stone space and R is a continuous quasi-order, we'll call that a descriptive S4 frame. So stone duality gives you a full categorical duality between Boolean algebras and stone spaces. All right, and in the same way, and this really is vastly more general, we get this dual equivalence between the S4 algebras with homomorphisms and these relational spaces, which we'll call the category of descriptive S4 frames. What are the morphisms in that category? Well, obviously they should be continuous maps because the set has topological structure. They should also respect the relational structure, and the notion for that we call a p-morphism or a bounded morphism. And basically, so a map like this is p-morphic if it preserves and reflects the relational structure, right? So if I have two related elements, they should map to related elements. And if I ever have these two solid arrows in the diagram, I can complete the square with the dotted arrows.
P for pounded, or?
I don't know. I honestly do not know. If someone here knows where the name p-morphism comes from, I mean, it comes from modal logic. These were studied for a long time. I do not know why they're called p-morphisms. Maybe bounded morphism is a better name, but still. Yeah. Okay, so we have this full duality, and that's how I'm actually thinking of these algebras. And so I will often sort of blur the line, right? If I'm talking about an algebra A with B diamond, then I'll refer to the dual frame or the dual space of A as just this descriptive frame, which is a topo relational space, right? So like a stone space with relational structure. And we have a duality, right? So you expect that injective maps correspond with surjective maps. So subalgebras on the algebraic side can be identified with appropriate quotients of the spaces, specifically these quotients by, the compatible equivalence relations that are the kernels of the morphisms, right? Because we're dual to an algebraic category. And in the same way, quotients or homomorphic images of the algebra are going to correspond to subframes on the other side of the duality, specifically these special kinds of subframes. We won't need the details there too much. This seminar is full of algebraists, so you'll like to know what the subdirect, irreducible, and simple algebras are across this duality. There's a very nice characterization. So in the dual relational space, you say a point is a root if it sees everything, and we'll say that the space is strongly rooted if it has an open set of roots, which will actually turn out to be cloval. If that's the case, right, so then we have our characterization. Subdirectly irreducible algebras are exactly those whose dual spaces are strongly rooted. And the simple algebras are exactly those whose dual spaces are just an R cluster. So in other words, every point sees every other point. So, right, now that I have this duality, I can talk about the notion of the depth of an algebra by meaning something about the relational space on the other side. So if you give me an S4 algebra A, I'm going to talk about the depth to mean the longest length of a proper R chain in the dual relational space. And of course, there could be no longest length, and we'll say it's depth omega in that case. We can extend this notion to varieties, right? So I say a variety of S4 algebras has depth bounded by n if the depth of any algebra is bounded by n. What's more interesting about this notion is we can actually control it with identities. So if you inductively define this little family of formulas here, you have this result that an algebra or a variety validates the identity Pn. Exactly if its depth is bounded by n. And more interestingly, you have the Segerberg-Maximova theorem, sort of a classical result that completely characterizes the locally finite S4 algebras or locally finite varieties of S4 algebras as exactly those with bounded depth, right? So to clear this up a little bit, I have on the next slide just a picture of the entire subvariety lattice of S4. Missing some details on the picture, but you know, it's good enough. So here's the rough picture. So at the top, you have S4, and then I'm using this notation. So brackets in means to impose the identity that bounds the depth by n. Right, and these GRZ stands for Gregorgic. So these Gregorgic 0.3 logics are exactly the minimal varieties of depth n for any n. And they are actually these Gregorgic 0.3s are actually just the variety generated by the algebra of just an in length chain. And so what the theorem on the last slide says is that it's exactly the locally finite varieties are exactly the ones below the dotted line, and the ones above the dotted line are not locally finite. And so actually what we get from this, since Gregorgic 0.3 is the unique minimal variety of infinite depth, we actually get decidability. So if you give me a variety of S4 algebras, say presented by identities, I can decide if it's locally finite. All I have to do is decide if the variety includes Gregorgic 0.3, which if you turn that around, right, that would just means that I need to show that the axioms of Gregorgic 0.3 prove the axioms you gave me. And S4 is a decidable logic, so I can do that, right? So we get an algorithm to decide if any given variety is locally finite. Okay, so let's finally talk about then monadic S4 algebras. So all the intuition to understand these, you have from just, they're very much like S4 algebras. So we have another unary operator. So we have a tuple this time of Boolean algebra, and then a closure operator diamond, and then E. So yeah, what are the rules here? So again, diamond is an S4 operator or a closure operator. And this E is going to be an S5 operator, which is just an S4 operator of depth 1. So it's an S4 operator that satisfies this P1 from one of the previous slides that essentially asserts that its dual relation has depth 1. We'll see that on the next slide. And crucially, you have this left commutivity axiom that says that my two operators interact in a reasonable way. So you have this identity here of left commutivity. And just as we write box for the dual of diamond, which will be a closure operator, or sorry, an interior operator, we will write for all for the Boolean dual of E, which will be another interior operator. So why would we look at these? Well, so these provide or can provide semantics, or can be viewed as semantics for the one variable fragment of predicate S4 logic, right? So if you start with a propositional logic like S4 modal logic with the box, there's a standard way to add quantifiers to it and to get a full first order version of that logic, which I would call QS4. And so if you do this and then you look at only the only unary predicates and you're only allowed to quantify over a single variable, we would call that the monadic fragment. And the translation of how we're thinking of formulas as representing monadic first order formulas is like this example here. So for example, the left commutivity axiom that I wrote can be viewed as like a first order statement like this, as a statement about how quantifiers interact with your modality. And these are justified in being called semantics for this monadic fragment because we have this translation theorem that this translation sort of preserves and reflects theoremhood. So this is really modeling monadic first order S4. So what do the dual spaces look like? So to generalize the duality picture, so what we have now are descriptive MS4 frames. So now you have a stone space, you have a continuous quasi-order, just like before, and now we have an equivalence relation as well, which you'll note is just a quasi-order of depth 1. Reflecting the fact that E was an S5 operator instead of just an S4. So again, you have this R and E, and they left commute in this way, and reading that statement, RE is contained in ER is I hate that notation. I'd rather just think about it like the picture on the right. The commutivity rule says that if any member of an E cluster sees somewhere else, then every member of that E cluster has to see there. All right. So if my E neighbor R sees into this other E class, then I'd have to see into that E class as well. So we get a full dual equivalence again between the category of MS4 algebras with homomorphisms and these descriptive MS4 frames. This time the morphisms have to be obviously p-morphic with respect to both of the relations. And the punchline here is, of course, that every MS4 algebra can be thought of in this way as the algebra of Clobin subsets of this kind of relational space. Right, and the diamond is saturating under R inverse, and E is saturating under B. Okay, so if I have one of these algebras, okay, so here's a relationship with S4 algebras. It's kind of a nice relationship we have. If I look at the exists or for all fixed points, those will be the same. So I look at the set of E fixed points, and then I let diamond 0 just be the restriction of the diamond to that set of fixed points. Then what we get here is actually an S4 subalgebra of the S4 reduct of B diamond. This crucially depends on that. This follows exactly from that left commutivity axiom, if you work it out. And we can interpret this exact same situation dually. So what this statement up here means dually in the relational spaces is that E is actually one of these compatible equivalence relations that I'm calling a correct partition. So you can take a quotient by E, and then this the relation R will sort of be well defined on the quotient in this way. And what you'll get out of that construction is exactly a descriptive S4 frame. So this is one way to start with an MS4 algebra and just get an S4 algebra on the E fixed points. So another sort of way that you can compare this to S4 algebras. So you want to characterize subdirect irreducibility and simplicity again. So what we can do is in an algebra, you can define the composition of these two operators. We'll call that black diamond. That is going to turn out to be an S4 operator. The dual situation here is that we just define this new relation Q to be the composition of R and then E. So a quasi-order composed with an equivalence relation will again be a quasi-order. So the punchline here is we can pretend as if this black diamond is an S4 or a closure operator that dually corresponds to this relation Q. So like the operation black diamond is given by Q inverse in the dual space. And again, we have black box, which is the dual interior operator. So with this notion, this turns out to be the appropriate notion to get this characterization of these things again. So you have that A is subdirectly irreducible if you're strongly Q rooted. So you need an open set of Q roots. And you're simple exactly if every point of X is a Q root. So the situation is identical there to the situation for S4 algebras, except we're using Q instead of R. Okay, so that's interesting. I don't know why that's not grayed out. That's fun. So a variety, we'll call it semi-simple if, and sorry you guys can't see this, if every subdirectly irreducible algebra is simple in that variety. So this is right. So every simple algebra is subdirectly irreducible, but the converse is not generally true. When the converse happens, we'll call that a semi-simple variety. And if you think about what this characterization from the last slide shows, you need so if subdirectly irreducible is going to be simple, then any Q rooted dual frame will actually be a Q cluster. Or in any dual frame, Q has to be an equivalence relation for that to happen. And finally, what that means is that the relation Q should be a quasi-order of depth 1, which we know that we can assert with this identity just in the black box and black diamond that says that Q has depth 1. And so that motivates this definition. So we'll call this MS4S. This is going to be, so you impose the identity that asserts that Q is a quasi-order of depth 1. And it turns out that this is the largest semi-simple subvariety of MS4. So something we do is we demonstrate that this MS4S, which generalizes a few well-known logics, this MS4S is finitely approximable, which means it's generated by its finite members. And what this turns out to mean on the logical side is that the logic of this variety, or its equational theory, you might as well think of it, we have the finite model property and we have decidability. All right, so we can decide the entailment relation for MS4S. So yes, this generalizes, this fact was known for these two logics that are actually, well, either subvarieties of this MS4S, or logically they would be extensions. But yes, these two other logics were known to have this property, but this variety sort of contains both of them, and it's a proper generalization of that. We won't need the details on this S4U, but we will talk quite a bit about this S5 squared shortly. So when we have MS4 algebras, we'll talk about their depth, and by depth I mean exactly the same thing that I meant for S4 algebras. So I'm going to mean the depth of the S4 reduct, or equivalently just the R depth of the dual space. And so it's, you know, the first question you have is, well, is local finiteness directly characterized by depth again? The answer is very much no. And it fails already in depth 1. So this MS41, so that would assert that this MS41 asserts the axiom that says that R is depth 1. So if you think about what that means, so you have a quasi-order and an equivalence relation. You've just asserted that your quasi-order is actually depth 1, so it's another equivalence relation. So you have this S5 squared situation, which is basically you just have 2 commuting equivalence relations in your dual space. And so this MS41 is identified with a variety that people normally think of as S5 squared, because you have 2 S5 operators. And this was the fact that this variety is actually not locally finite was first noticed by Henkin, Monk, and Tarski when they were studying cylindric algebras. Because it turns out yet another name, a third name for this same variety is, you might think of it as the variety of 2-dimensional diagonal-free cylindric algebras. Again, we won't need the details, but that's also what they are. Right, so in these S5 squared frames, the relations, right, you have basically now 2 commuting equivalence relations in this situation. And I think it's informative to see this example of Henkin, Monk, and Tarski. What they did is they demonstrated a 1-generated and infinite subalgebra of this. So basically take the grid omega cross omega, and your algebra is the power set of that grid, and your 2 operators are you're allowed to saturate by rows or saturate by columns. Right, so the equivalence relations close under row or close under column. And using these operations, the example is that this red triangle that I've drawn here generates an infinite subalgebra, and I'll just roughly show you how that goes. Right, so you start with this red triangle. I take a complement, and then I close under column, and then I take a complement again, and then I subtract that from my original generator to get this triangle, and then I close under rows, and then I take a complement. Now I got earlier the first column, now I have the first row. I intersect that to get the singleton at the corner, and that bootstraps you. You can get off the ground and actually generate every singleton this way. So that is how you get this 1-generated infinite subalgebra. So what we did actually, so this picture here is an S5 squared frame, but it's not a descriptive S5 squared frame because I'm just considering this with the discrete topology. It's not a stone space or anything. So something we did is we actually just went to the effort of characterizing the dual space of this 1-generated subalgebra to get a more explicit example. So basically what we did is we characterized exactly the dual space of this 1-generated subalgebra. And if you just kind of like took a random guess at what it would look like, this might be the picture that you end up with, because you basically have added compactification points to the end of all the rows and to the end of all the columns. And you have actually these 2 compactification points up at the corner. So this square is to indicate that this K1 and K2 are in both of the relations, right? So K1 is row and column related to K2. We sometimes call that a bicluster. So this is exactly the dual space. So this gives an explicit example of a descriptive MS4 frame that is exactly it's a 1-generated algebra and it's infinite. And the topology here is actually pretty interesting. We describe this as a certain sort of 2-point compactification of a locally compact space to get this picture. So anytime I have a quasi-order, I can talk about its layers, right? And how I do that, right, is I could just take the maximal points. Now, you may complain already that just for an arbitrary quasi-order, there may not be any maximal points. That's totally possible. It turns out they will in our context. And so some of these DIs may be, empty for a random quasi-order. but you can still define them, right? You can take the maximal points and then throw those away and look at the maximal points of what remains and so on. And in this way, you get layers of the quasi-order based on sort of distance downward depth away from the maximum. It turns out that in descriptive S4 frames, this D1 or the maximum exists. It's non-empty and it's a closed set, which is nice. And even more is true if you have a finitely generated algebra. Then in the dual space, you'll find that every layer of finite depth is actually clopen and consists only of isolated points. You only have non-isolated points sort of in infinite depth. So what the last example shows is that already the situation is more complicated here because we just saw an MS4, descriptive MS4 frame of depth 1. So it only has a maximum layer. But that layer was, it already contained limit points. And we actually have no idea if the second point here. So the first case does not, well, the first case generalizes. We do not know if the second case generalizes here. We suspect that in a finitely generated algebra that the layers of finite depth will be clopen, but the techniques to prove that sort of just break down completely in the bimodal setting. So we do not know. And we're also interested in knowing if you can construct an MS4 frame whose layers only consist of limit points. So like somehow every point on a layer is like a limit point of stuff beneath topologically. We don't know if that's possible. We'd like to know. So already it's harder to establish these nice structure facts about finitely generated, the dual spaces of finitely generated algebras. So it's a fact that every proper subvariety of S5 squared is locally finite, which is really nice. So S5 squared is literally the only non-locally finite S5 squared variety. And when you have these MS4 algebras, if you look at any layer of the relation R and you restrict the equivalence relation to that layer, then you get on that layer two equivalence relations. And so one might be led to this reasonable conjecture that if a variety is going to be locally finite, then it should be finite depth. That's definitely necessary because if it wasn't, then already the S4 reduct would fail to be locally finite. You could just generate infinity in the S4 reduct. And so you kind of like, you know, morally, you want to impose that you're finite depth and you're somehow finite width, which should say that the layers should form a proper subvariety of S5 squared, basically. So something we show is that this conjecture fails drastically, but I'll go over some positive results we have, and then the last part of the talk will be about another subvariety of MS4 where we think we do have such a characterization. So first, the positive results here. So we have this characterization that is admittedly not very useful. So if you give me a subvariety of MS4, it is locally finite if, of course, it's finite depth. That's necessary. And then what you need is a uniform bound so that if I give you an in-generated subdirectly irreducible algebra, then this S4 subalgebra, or the algebra that I was calling A naught, will be f of n generated as an S4 algebra. And this condition sounds a little bit opaque because it is. It's hard to check. It's very hard to check, but we did manage to use it to get this result. We have this, I'm not going to bother defining the formulas here, but we identified this family of formulas that we call alt 0k, just a modification of the modal formulas alt k, if you're familiar with those. And we show that for these varieties, for any k, then these will be locally finite exactly if they're finite depth. So for this family of varieties, the S4 result does generalize exactly. And one notable member here is that alt k1, actually, if you impose the identity alt k1, then that's exactly the variety known as S4U. This is the logic of S4 with a universal modality, but that happens to be a special case of this. Okay, so now to generalize the negative results, I need a little bit of background. So S5 subscript 2, which I will read as S5(2) instead of S5 squared, is very close to what we've already been talking about. It's the variety of these S5(2) algebras. Can I move this here for a second? So you have in an S5(2) algebra, you have these two closure operators. So it's just like S5 squared. You have two S5 operators or two equivalence relations, except there is no commutativity axiom at all. We have here two completely unrelated S5 operators, and the dual spaces are relational spaces with two equivalence relations that have absolutely nothing to do with one another. And as you might imagine, these can be pretty complicated because, one equivalence relation is easy to understand. Two equivalence relations that have absolutely no compatibility relationship with each other, very hard to understand. It's sort of like, one bit of information you can't do very much with, but with 2 bits of information you can make, the internet. So a similar sort of thing happens here when we have these two equivalence relations. They can interact in very, very complicated ways if you don't have any commutativity axiom at all. And logically, so this would be referred to, so S5 squared would be the product of S5 in itself, which is where you have two S5 operators and you impose commutativity, right? And S5(2) is what we would call the fusion. So it's just, now we have two S5 operators and they have nothing to do with each other. So below here is just a picture of like, some unexpected, right? These S5(2) frames can be whatever, right? So when the relations don't have to commute. So, if I'm thinking of S5 squared frames as grids, like we saw on the other page, where I can get, if I can go right and up, I can go up and right. That is not the case here, right? So both of these pictures, I'm still going to use vertical lines to denote the equivalence classes of, I honestly forgot which one I think of as vertical, but let's say E2 will be vertical lines. So every vertical line in these pictures is an equivalence class of E2, and every horizontal line is an equivalence class of E1. And that's kind of how these things work. You can see in these pictures, right, the relations don't commute. So all of that to say that S5(2) fusions are, in general, wild. Once you just add two operators and you had no axioms at all saying that they're reasonable with respect to each other, then these things are really bad. So, in particular, local finiteness in S5(2) is wide open. Fusions drastically do not preserve local finiteness. It's known we have sufficient conditions that will guarantee that the fusion of two locally finite logics will be locally finite. But in general, those sufficient conditions are highly restrictive, and so basically nothing's known about the general case. So all this to say, S5(2) local finiteness is very hard to understand, wide open. So what we do for a negative result here is we actually demonstrate a translation of S varieties of S5(2) into varieties of MS4, but not just varieties of MS4. Our translation actually lands in MS4S of depth 2, which is like as restrictive as you can get. So not only does the target produce a semi-simple variety, and it produces a variety with depth bounded by 2. So already in this case, so this translation has the property, right, that V is locally finite as a subvariety of S5(2), if and only if T of V is locally finite as a subvariety of MS4. And so what this translation demonstrates then is that characterizing local finite is sort of like a reduction, right? It demonstrates that if you want to characterize local finiteness, even in this very small subvariety of MS4S or MS4, that's already as hard as characterizing it in S5(2). So here is the proof in one slide. I will attempt to explain with the words. So on the top here, what I have is an S52 frame. So again, horizontal lines are E1 equivalence classes, and vertical lines are E2 equivalence classes. They're drawn in blue. So if you give me any such frame like this, then what I can do is just, let's say, pick my vertical relation, E2. I'm going to turn this into an MS4 frame by stretching out, by adding verticality to these E2 classes. So what you do is you just slap on a top rail. You put an R cluster up here in the top layer, and then you make your second layer basically exactly the same as the original frame that you had. And you stretch these, so these equivalence classes now are, they contain their corresponding point in the top rail. You'll notice here that I can generate, starting with the singleton on the left, I can generate an infinite subalgebra in this S52 frame, right? I just saturate with E1 and then saturate with E2 and then saturate with E1, right? If I do this, I keep picking up points. And so the same is true here. So you do this construction in such a way that it's a disjoint union topologically. So the top layer, you have access to it because it'll be a cloven element of the algebra. And then just by doing relative intersection, doing everything relative to the bottom layer here, you can do the same. You can make the same one generated infinite algebra in this frame. But this frame, if you'll notice, is very tame as an MS4 frame because it's actually a Q cluster, right? Starting from any point, I can get to any other point via Q, which is R and then E, right? All I have to do is R up to the top rail and then travel along this R cluster to wherever I want, and then E down to the to any other point. So this is why the translation lands us in MS4S of depth 2, because the target of this construction here will actually turn out to be it'll be a 1 Q equivalent. Every point Q sees every other point in this frame. So that's the idea. And something we realized recently is actually this construction. One way to think about MS4 is that it's the expanding relativized product, which basically just means you have an S4 operator and an S5 operator, and you impose left commutivity, which is how we defined MS4. If you want the full product of S4 and S5, that would mean that you insert a full commutivity axiom between the two. And we can actually alter this construction so that this extends to the full product, which is important because products were thought to, generally, we have a better hope of understanding products of algebras than just these semi-products. But our construction actually extends to the full product. And so here's just one more example demonstrating that it's not even sufficient. So local finiteness, the situation does not come down to whether or not all of your layers are locally finite as S5 squared or as S52 algebras. And this example demonstrates that, because if you look at the top layer, it's so for reasons that I won't go into, each of these layers, if you look only at these dotted rectangles and restrict the equivalence relation to that layer, then what you get is in each layer going to be a locally finite S52 algebra. But nevertheless, I can generate an infinite subalgebra in this whole thing just by starting with the singleton G, right? What I do is I saturate with R inverse, right? So that picks up this point, mouse, to pick up this point, and then saturate E, and then subtract the top layer to pick up this point, and then saturate R inverse again to pick up this point, and so on. So all of the layers here are locally finite, but this whole algebra fails to be locally finite. So basically the situation, in even in MS4S2, already in depth 3, is very complicated. It doesn't come down to the layers at all. So I mentioned before that there is another natural subvariety, which I'll get through in 5 minutes, where we may have such a characterization. So to motivate it, I won't go into these here, but these formulas are known to people who study intuitionistic predicate logic. Of course, these two formulas that I've written here are tautologies of classical predicate logic, but they are not tautologies of intuitionistic predicate logic. And so both of them give rise to distinct, what we call intermediate predicate logics. And the top one is strictly weaker than the bottom one. So why are these formulas natural? So we have this translation that's been known for a long time, where if you take intuitionistic propositional logic, you have the Gödel translation into the Gregorgic logic, which is a subvariety of S4. And then the splitting translation takes you to the Gödel-Loeb logic, which by Solovey's theorem, you can actually think of this Gödel-Loeb logic as the logic, you can interpret the box in that modal logic as the Peano arithmetic provability predicate. So in that logic, like box P literally means it is provable in Peano arithmetic that P. And so what this shows is like this is one of many ways to justify intuitionistic propositional logic, right? Since it can literally be interpreted as provability, that lends credence to the sort of constructivity or the BHK interpretation, sometimes called of intuitionistic logic. If you go to the monadic setting, so this MCAS would just be the monadic formula, so take out the x's, right? Those are just monadic formulas, so this is the modal version of that formula. And if you perform the Gödel translation on it, you get this thing. And again, this black box is just a box for all. And so recently, Beznashvili, Brantley, and Elin showed that these formulas are exactly what you need to extend that translation on the previous slide up to the monadic setting. So basically that entire translation lifts. It doesn't lift to MIPC, to monadic Gregorgic, to monadic Gödel-Loeb, but it does lift if you assert these Casari formulas in those two logics, then you have this translation. And so this Casari formula is sort of crucial to get a provability interpretation of the monadic fragment of intuitionistic predicate logic. So that's why this formula is interesting. So then it's natural to examine this variety that I would call M plus S4, where I just assert this Gödel translation of the Casari formula. Already things are much, much better because roughly there's a caveat that I'm not going to go into here. This axiom, asserting this identity, essentially prevents your dual space from having what we call dirty clusters, which is an E class that contains two properly R-related points inside of it. So this picture on the right here is a dirty cluster. And you'll notice that these horrible counterexamples from the previous slides sort of very, very crucially rely on like all of these are dirty clusters, right? You have to have, you're always going to have properly R-related points inside the same E cluster. So already that doesn't happen, which rules out all of the bad counterexamples. And we already have much better structure. So in a dual space of an M plus S4 frame, every layer of finite depth will actually be E saturated. And so instead of being an S5 subscript 2 frame, it turns out to be an S5 squared frame. So the restrictions of the relations on each layer actually commute. And this also drastically differs from the MS4 situation. We have a unique minimal subvariety of infinite depth again. So let me finish here with this. This is exactly the subvariety where it appears we're going to get the characterization we want. In the sense that you're locally finite if you're finite depth, which is decidable because of this unique minimal variety. And this certain other variety, V sub t, which is an S5 squared subvariety, is locally finite. And I'm not going to put the definition here, but basically this is capturing a finite width condition. So this V sub t is generated basically from the layers of your algebras in V. And we're currently trying to decide if this part 2 of this theorem is decidable, which would yield sort of decidability of the whole thing. and would be a really nice analog of the Segerberg-Maximova theorem. So that is it. Thank you very much.